Okay, so let's talk about 11.1, which is called geometric sequences. It's not geometry. Don't worry. I promise it's not geometry. Do you guys want to see the geometry?
No.
Okay, so let's try maybe an example with numbers, which will be a bit confusing, and then we'll look at some picture to see if we can maybe understand why you would do this.
Can we have a regular
Cool.
problem and then a really easy problem? No. Let's just do the
Maybe not really easy. All right, so let's think about this kind of idea. So this is an idea that comes out of a couple areas of science, but maybe the easiest one is half-life. You guys know what a half-life is?
video.
It's a video game.
It is.
Okay, good. What's half-life when it's not a video game? Yes, it's a video game about zombies. That's true. Aliens.
Radiation or something like that.
Yeah, it's something about radiation or something. Maybe?
Yeah.
Okay, so what half-life is you start with some kind of a blob of something, right?
Okay.
Radioactive stuff. Okay. And then after a bit, right, a half-life happens. So this is kind of a,
Is that like 50 years?
maybe. Some amount of time passes, and then you're left with half as much stuff. Okay, so stuff.
Less.
Now we have stuff over 2. Does that make sense? So really, if I was just going to
Oh,
call whatever stuff I had, if I just called that 1, right? Then some time passes, and then there's half as much stuff.
And then more time.
Yeah, so what happens if time passes again? Yeah, I have stuff over 2, right? Which reduces to stuff over 4. So that's my half turns into a quarter.
So is it just 2 quarters there, just continuing that curve?
Yeah, you guys see that? So time passes again. I get, oops, that should be small, right? This should be stuff over 8.
Why not?
Why not 6?
Oh, because it's. No.
Yeah, because this is multiplicative, right? Okay, so this one turned into an 8th. That turns into a 16. And kind of so forth, right?
Why they call it geometry? If it's not geometry.
It kind of is geometry. The sort of geometry that I'm doing, it looks a little funny with these blobs, right? But really the geometry I'm doing looks like this. Here's a square, right? If I cut it in half, right? This is, so the whole square was the 1 unit. I cut it in half, this is the half. If I cut that in half, this is the quarter. If I cut this in half, this is an 1/8, a 16th, right? A 32nd, a 64th, and kind of on and on and on, right? You guys see that? Okay, so what I'm really doing is I'm talking about this geometric rate, which is just cutting it in the same number of pieces and collecting those pieces every time. You guys see that? So this is what we call a geometric sequence, where I just proceed from 1 to a half to a quarter to an 1/8 to a 16. Cool? You guys good with this? Let me ask a stupid question. What if I started with 7 things? So if I started with 7,
What?
then the next step would be
14. No?
Seven over 2. Is it always going to be 1/2, or is it going to tell you, like in the problem,
It depends. Half-life isn't
You know
the
what I mean?
Yeah.
Okay.
Half-life isn't the only thing this is good for,
Okay.
but I can solve half-life problems, and sometimes they're not phrased as the half-life is X years or something. There's a way I can figure this out kind of regardless of,
What it's called.
yeah, and actually with a bit less information than what the half-life is. If they tell me how much there was, how much time passes, and how much there now is, I can get away with doing math on that. That's a sort of down the road thing. Right now, I just want to say, if I started with 7, say, pounds of plutonium, and a half-life passes, how much do I have at the next stage? 7 over 2. Yeah, I divided it in half, right? So each of these steps that's happening, right? This step, I should think of as a half-life. You guys see this? So at the next half-life, I'd get 7 quarters. At the next half-life, 7 over 8, and kind of so forth. So I'm going to call these things, I'm going to call this a geometric series. I'm going to call this thing a geometric series 2.
It's just the same shape.
Okay, so these were half-life geometric series. There may be other options here. You guys want to see another thing that I'm going to call a geometric series? Yeah, we might call a quarter life a geometric series. So how would that thing work? Yeah, I'd take my kind of starting number, right? And then I'd proceed to, yeah, number over 4, right? Then I'd proceed to my number over 16. Very nice. And then I'd proceed to number over 64. Why is it 64? 16 times 4, or 4 cubed, right? You guys see that?
It's just, you take the two numbers and then multiply them together, and then the two numbers and multiply together.
Kinda. So let's talk about what we're doing. So this guy is number over a bigger number, which is 64 times 4, whatever that is, or 4 to the 4th power. You guys see that? What's the next one going to be? Number over 4 to the 5th. You guys see that? Okay, so each of these arrows represents either a passage of time or, at the very least, as a function. These representing multiply by a quarter, right? You guys see that? What were the arrows over here? They represented half-lives or as functions. Yeah, multiply by a half. You guys see they're all the same thing? Right? Each arrow represents the exact same function. So what I'm doing is I'm really starting someplace and then looping a function on it. Okay, see that?
Can you do the same thing to make it bigger?
Oh, that's a great idea. So could we make the same kind of idea, but make it get bigger? Yeah, I don't see why not. Let's say we start with the number A. What do you guys want to multiply by? 2. 2? Sure. 2 seems like a good place to start. So I get 2A. Then what do I do? 4A. Then I get, is it 6 or 8?
8.
Show of hands first. 8? Show of hands for 6? Nobody? Because it's the 2 and the 4 and they multiply. Yeah, very nice. What's the next one? 16.
32.
A, right? And then I get 32A. So here I could think, right, this is 2 to the 1. This guy is 2 to the 2. This dude is 2 to the 3. This guy is 2 to the 4. 2 to the 5. What was this first one? Oh, that's why we want to make it 1, right? So this is counting like a computer person. Start at 0. Did you guys know that? Lots of computer science programming type people start counting at 0 because computers start their loops at 0. They start their loops at 0 because we want to make this easy to code. Because this is kind of, well, this is how money grows, this is how populations grow, this is how radioactive decay works. This is sort of one of the fundamental science-y things. What's up?
Okay, so it's off of my initial statement that it's just whatever 2 are closest. It's whatever is the last number multiplied by the first number, right?
It's whatever the last number is multiplied by the growth rate.
Well, like, okay, so it wouldn't be for the 64 number over 64. It wouldn't be for the next one 16 times 64. It'd be 4 times 64.
Yeah, it's a little bit like this first one tells you what the growth rate is.
Yeah.
You guys see that?
And so then the next one would be whatever that times 4. And you always go back to the first one.
Yeah.
Okay.
Okay. So if I wanted to write down a definition for what a geometric series is, okay. So my definition for a geometric series is going to start with the idea of given a pair of numbers, okay, there's going to be an A, and for A you can think starting point. And then there's going to be an R, and for R you can think growth rate. Okay, so I'm given a pair of numbers, A and R, which I would like you to think of as a start point and a growth rate. So I start at A. And then what's the next element in my list? A times R. Good. You guys all see that? So I start at A, and then I multiply by whatever the growth rate is. I get A times R. Okay. What's the next one? You guys see that the commas are shorthand for the arrows? A, R, AR times R, right, which is AR squared. What's the next one? AR cubed. What's the next one after that? AR to the 4th. AR to the 5th. And so on, right? Cool? Okay, so given a pair of numbers, A and R, there's this thing, and I'm calling that is a geometric sequence. You guys cool with this? So the word we're defining is geometric sequence. And what we mean by that is this progression. You guys cool with this?
Would you only use this with like radiation and stuff?
We use this with lots of stuff. So there's a book, or there's a problem in your book about zombies. that you apparently missed? Yep. It's number 80 something and 10 point something. There's a video of it on the YouTube channel. You might want to go look at that.
I probably would.
It's phrased as an epidemiology question. It's like one person is infected, they infect 4 new people. Each of those people goes out and infects 4 new people.
But how would you
That's geometric growth. That's why we call this a geometric sequence, because it grows at a multiplicative rate.
So if you were to end
What's
up
that?
drawing that, would it kind of look like 3 roots?
Yep. Yeah, if you drew what the epidemiologist diagram looks like, yeah, it looks like tree roots.
I like
Okay, cool. You guys good with this thing? Okay, there's a word of caution here that I have to get in, because a lot of you are going to tend to lump these 2 words together. So, I'm going to define something else, which is a little bit similar. Okay, and the only reason I'm defining it is so you don't screw these words up later, because it's really easy to. So, there's this other thing, which is a geometric series. Okay? You see how confusingly worded this is?
Yeah.
Yeah. So a sequence is a progression, and a series is a sum.
I thought it was a collection
A
of
sum. So a geometric series is something like A plus AR plus AR squared plus AR cubed, and so forth.
In other words, the series you add, the other one you multiply.
No.
No?
So these guys are just listed.
Oh.
Okay, so the big thing here is this gadget. Oh, wow, horrible. This whole gadget, this definition, is really about a list. Okay? This whole gadget here is about a number. Right? The result of what you get when you add all these things up. You guys see that? I'm not going to talk about these other than to say this definition today. Okay? There's a good reason you would want to do this. And later we'll try to probably play with this. But for right now, I just want to point out that there's this similar object that's talking about a number, and it has plus signs in it. And what we're going to talk about today and for the next couple of days is lists. You guys cool with this? All right. Good. Please put these words on a flashcard or something so you don't mix them up, because they're easy to mix up. Cool? All right. So let's maybe see if we could do an example or 2. This is kind of a game that we're going to play. Is this a geometric series? Oh, sorry, sequence. See, I told you, the words are very hard to mix up.
Are we going to get in trouble on the test if we mix up because we missed it?
Yes. Do as I say, not as I do. All right, so let's have a listing.
That was tricky.
Is that a minus sign? Oh,
Yeah.
I see.
It's 2 negative equal.
Yeah.
Okay. Let me put down a couple more of these. Okay, so I want to check, is this a geometric series? If it is, what's A and what's R? Cool. So, okay, how about this first one? Show of hands for yes. Okay, most of you. What are A and R? A is 2.
R is a 2.
R is also 2. You guys see that? So the A you can read off the start, right? And then this divided by that is going to be the growth rate if it's the same, right? So then I should check, right? So I take this by that, I get R is 2. And then I check, okay, did I multiply by 2 to get here? Yep. Did I multiply by 2 to get there? Yep. Did I multiply by 2 to get here? You guys see that? Okay. How about this guy?
Well, if you don't have any pluses between them, then they're going to be a sequence, right?
So these can be sequences that aren't geometric.
Oh.
Right? I'm not asking for the difference between a sequence and a series here.
Oh, okay.
I'm asking, are these geometric sequences or some other kind that I don't know about?
Oh, so far you just showed us.
Do you guys want another example of a sequence that's not a geometric sequence?
No.
Well, is that?
It's any numbers that aren't a sequence. I mean,
Yeah, numbers that just don't follow the rule would be a perfect one.
Like
Oh, like which one of these isn't?
the 4, 8, 12,
4, 8, 12, 16. You guys see that?
Is that
What would the A be?
the 8 would be adding.
The A would be 4, but
There's no, well, the R is
the R would have to be 2 from these guys, right? But twice 8 isn't 12. You guys see that? Okay, so what's the rule here to get from one thing to the next? Yeah, it's add 4.
Which is this one.
Do you guys see
So
that?
is that a series?
So this isn't a series because the terms aren't added together, right? It's still a sequence. But the rule isn't multiplication, it's addition.
Okay. So would we write rule of addition in there for like an answer?
Okay, so you could say not geometric, right? It's not a geometric sequence. There's a word for this one. What's the fancy math word for addition?
Addition.
Starts with an A.
Addition.
Arithmetic.
Oh, I thought that was just.
This is an arithmetic sequence. I don't care if you know that word, but as opposed to a geometric sequence, this one is arithmetic.
Would it be the same for the like half, 1/3,
Is there an addition rule between the terms in that one?
1/3? No.
No. It's a sequence. It's not geometric. It's also not arithmetic. This one here has a special name, but it's not a geometric series or a sequence. God, I keep saying that. Not a geometric sequence. This one's special name is harmonic.
It's in harmony.
Yeah, there's some kind of a music thing to this. I don't know what it is.
We like quarter notes. Yeah.
Yeah, like I said, I don't know. There is some kind of a music interpretation here. This thing's actually very important, so that's why I'm kind of highlighting its name. This one has a name. It's not a geometric sequence. You guys see that? How about this guy?
But it's some other
It's
guy.
plus 2.
It is like 2.
4 plus 2, 6. six plus two is two. You're adding two.
This one's weird, right?
Yeah.
Because you're not adding something, you're adding something to just the bottom, right?
Yeah.
Like there's a predictable rule to this one. This one's also not arithmetic or geometric. It's weird, right? It's one of the other guys. So this is not a geo. It's also not arithmetic. Cool?
But we're not trying to write that it's not arithmetic.
No, I don't care if you know what arithmetic means. If some of you take away what arithmetic sequences are, that would be great. But I'm not requiring that. All right, how about the last one?
But you're adding one at the bottom, so it can't be the same.
This guy?
Oh, that one.
We already did these ones, right?
That one, it is.
What's A?
A's
A is 1, and R is 3.
Yes. I like
So yes, it is. Oh yeah, we had this one that we didn't do still. Is it?
I know you multiply by 5.
So show of hands for yes.
Yes is what?
Show of hands for no.
But it's a negative, because
It
once you
doesn't
multiply it by another negative.
Say that louder, Jennifer.
2 negative equals positive and a positive equals negative and this is equals. Every other one will be positive and a negative.
You see that? That's very cool. So they can alternate between positive and negative. That means that the R is negative, right? You guys all see that?
So it would be a negative.
So this one has A is 1, right? And R is -5. What would the next sequence, or the next term in the sequence be?
What would be 5 times 5?
Be positive, whatever 125 times 5 is.
So, but it is one or it is not one?
It is, yep,
Okay.
this is. So we found yes, 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 no, no, no. Cool?
Break.
Do you guys want to take a break and then try to make some on your own? Cool. All right, take a break.